Linux in motion. This has been my personal mission for the last couple of years. Together with our automotive engineering team, the team that we proudly call our A-team, and many colleagues across the SUSE organization, we have made Linux in the car a reality. As of today, there are vehicles on the road that have a derivative of SUSE's enterprise Linux under the hood, not just in their infotainment system, but as the OS that runs the advanced driver assist systems. Those aren't just prototypes or test beds, they are serious production cars that you can order and buy. Over 20 years ago, SUSE invented the enterprise Linux distribution and brought professional support, multi-year maintenance lifecycle, and reliable roadmaps to the data center world. We are now first again, first to bring enterprise Linux to the vehicle. I'm Joe Werner, and I'm the Principal Product Manager for Automotive Edge at SUSE. In the next 30 minutes or so, I'm going to talk about why Linux in the car is a good idea, how we are doing it, but also why it has sometimes been a bumpy ride and why we think just Linux isn't going to be enough. Before we dive into the details, I'd like to position what we are doing in the automotive space on our product portfolio. In a nutshell, at the core, SUSE offers a comprehensive portfolio of generic enterprise Linux and offerings that are tailored towards specific use cases like running SAP, retail and point of service, and edge deployment. With those offerings, we address the needs of software developers, data center operators, cloud providers and users, and operators of operating systems that are deployed on site, at branches, or at the edge. Our operating system management and container orchestration solutions under the SUSE Rancher brand are a natural extension to the operating system portfolio and make managing application deployments from the edge or branch to the core to the cloud a seamless experience. Our edge solutions leverage these product portfolios and address the specific challenges of having to operate highly distributed infrastructures. We think that the generic challenges that customers have when they want to accelerate business innovation at the edge, like the lack of a consistent platform, security and compliance requirements, and high complexity also apply to the automotive domain. So our goal is to provide that consistent platform from the core to the cloud to the car, to help our customers address security, privacy, and compliance requirements that are getting more and more important in today's connected vehicles, and to help reduce complexity of the highly heterogeneous in-car software architectures. But first, let's try to better understand the challenges that the automotive industry is facing. We are only going to scratch the surface today. If you want to know more, my presentation from last year's SUSECON can be found on YouTube. The 4 mega trends that are changing the automotive industries are connected cars. Within the next 10 years or so, almost all vehicles will be connected to the internet. In many countries, at least basic mobile connectivity with automated emergency calls is the law now. And customers expect both a rich infotainment experience and always up-to-date map and navigation data. At the same time, new legislation requires that automakers provide cybersecurity updates to those connected cars, just like they are required to keep your smartphones secure. Autonomous cars. This is where many of the analysts and also quite a few of the players in the automotive market have been a bit over-optimistic. But at least under highly regulated conditions, on known mapped streets and at lower speeds, cars are going to be less and less dependent on the driver's attention. To reach the goal of partially or even fully autonomous vehicles, being able to rapidly improve the underlying software stack and to roll out new versions to existing fleets will become an absolute must-have. Shared cars. Car sharing, car rental services, and robotaxis will take more and more market share from more traditional models of self-owning a car or driving a company car. And finally, of course, electric cars or EVs. In some developed countries, EVs already outsell vehicles with a combustion engine, and this trend will certainly accelerate. Together, these four trends, usually abbreviated as CASE, will drive the adoption of mostly software-defined cars. Soon, more than one-third of the perceived value of a vehicle will come from its software stack. And just like you can update your phone or install new apps to get new features, car owners will expect their vehicles to get new features and bug fixes via over-the-air updates during the lifetime of the car. Regular software updates to fix security issues are the law now. Quoting directly from the website of the German Federal Motor Transport Authority or Kraftfahrtbundesamt, the UN regulations 155 cybersecurity and 156 software update introduce new requirements for manufacturers and technical services. In addition to the initial assessment of the manufacturer and the product testing by the technical service, the demonstration of implemented and effective dedicated management systems for cybersecurity and software updates is also required in order to obtain type approval. Now, each of those modern cars relies on dozens of small and not so small microprocessors or ECUs, electronic control units. And unless you've been living under a rock, I'm sure you've heard about the COVID-related chip shortages and dependencies on a more and more fragile supply chain. But not only that. Car manufacturers are also struggling with hiring all the talent they need to build those software stacks for their cars. There will be blood. That was the provocative title of an article automotive industry expert Peter Mertens published in 2020. He had analyzed how new players that are approaching building a car with the mindset of a software engineer disrupted the market, and he painted a bleak picture of the future of traditional car manufacturers. Earlier this year, after the first really competitive electric vehicles from some of the major large manufacturers had hit the market, he revised his view a bit. He now says, the empire strikes back. But the battles are still ongoing, and the automotive industry will need help with the transition from hardware-driven to software-driven designs. So, why is Linux in the car a good idea in that context? And how does it help car manufacturers? First of all, Linux is doing a really good job to abstract away hardware from software. And that is what the automotive industry needs to get less dependent on individual microchip manufacturers and hardware architectures. In the days of Unix, your OS came with the hardware, and although there were some promises of standardization like POSIX compliance, none of the vendors' operating systems was alike. Linux achieved for server and cloud what Windows managed to achieve for the desktop. Software can be developed once and run on all major platforms. Paraphrasing what one of our competitors put so nicely in a recent interview, the OS needs to be a stable platform so that everything else can change. So with Linux in the car, we'll address both the dependencies on specific hardware suppliers and the challenge of having to hire thousands of new software engineers. Because you'll be able to develop more, faster, with fewer resources by using existing proven open source software, co-developing the non-differentiating parts of your software stack with others, and reusing software for new projects, even if they are on completely different hardware stacks. Linux adoption in the car started a few years back in cockpit and infotainment use cases, displaying your dashboard navigation maps, allowing you to use a touchscreen to control settings like your air conditioning and so on. More recently, the first automakers have started to use Linux for more demanding scenarios, like in park assist systems. While the safety impact of Linux in entertainment isn't that high, those new scenarios require at least a strictly quality managed Linux stack. The ultimate goal is to be able to use Linux to replace proprietary operating systems that have been built with functional safety in mind. For drive assist systems up to autonomous cars. This is still work in progress. But there's one more step in the evolution that's already on the horizon. Next generation car architectures that imagine the car as an extension of the cloud. Let's call it the cloud native car. The first project SUSE has been involved in have brought a quality Linux that is based on our 20 years of providing reliable quality to the data center world, to the car. But we think that we need to go beyond just Linux. That's why the other area we are focusing on is helping to shape the next generation cloud-native in-car architectures. Of course, functional safety or making sure that the lives of everyone on the street, in the car and outside, are protected to the highest possible degree will also be essential to those next generation architectures. But we think that those new architectures will offer new approaches, not just copy the functional safety blueprints from existing real-time operating systems for safety. Okay, let's go back to the underlying goals the automakers have. Oversimplified, they need to develop new cars and new features faster to stay competitive. And they have to do so while improving cost efficiency. How can this be achieved? Now, the remarkable part is that the automotive industry already has the answer. Modularity, with pre-built interchangeable components that have well-defined interfaces. Until the end of the last century, new cars were usually developed as one-offs. Sure, successful engine designs and common third-party components would find their way into other models from the same company. And each model's next generation was usually just an evolution of the previous one. But there were lots of parts that had to be designed and manufactured to fit into one particular model only. Companies like Volkswagen changed this in the late 90s with their platform approach. From then on, cars of similar size from different brands within the same group, like Volkswagen, Audi, Seat, or Skoda, would use the same platform that was just modified enough to give those cars their brand identity. This concept was later refined with the concept of modular toolboxes, like the modularer Querbaukasten, a modular platform that can be combined in different ways to be the base for pretty much all the Volkswagen Group cars that have an engine mounted in a transverse configuration. Of course, they are following a similar approach with their electrical vehicle platforms, where different motors, battery sizes, and so on can be combined to meet the requirements of vehicles as different as a mid-sized SUV or a minibus. These platforms allow economies of scale. They can also be developed and improved faster because internal departments and external suppliers can work on components in parallel as long as they follow the agreed on dimensions and mounting point configurations. Now, many of the components of such a modern car are small computers. The current generation cars have dozens of electronic control units, or ECUs. Each of these ECUs has a very specific purpose. It controls fuel injection, manages the air conditioning, or is the brain inside an advanced sensor like a radar or a camera that can detect oncoming traffic or read speed limit signs. Those ECUs are typical embedded devices where the software is considered firmware that isn't really supposed to be messed with directly. If you're lucky, it can be updated as a whole. This may have been the right approach in the past, when each ECU had pretty unique hardware, and a large part of the firmware development was making sure that the hardware features are enabled correctly. Also, the firmware had to be really small and optimized. Any unused driver code or unused code in general was overhead that was ideally to be removed in the build process. But with the transition of more and more features of the modern car into software, this model falls apart. ECUs are hard to change once they are installed. Some can receive software updates during a service stop at the dealer or auto repair shop, but things are far from comparable to the flexibility and agility companies now have when they bring up new services for their customer-facing web or mobile applications as virtual machines or containers in a public cloud. The solution should actually be obvious by now. The automotive industry just needs to also apply the modular toolkit approach that has been so successful with their hardware to their software stack. But to make that happen, you need a platform. A platform that is the foundation the software can run on, that sets the basic rules and defines the interfaces, just like the modular toolbox defines where the mount points for the engine or rear axle should be. Luckily, no wheels need to be reinvented here. With enterprise-hardened Linux distributions like SUSE Linux Enterprise, customers can use common off-the-shelf certified hardware and innovate where it really matters, the application stack. Binary Linux distributions have been that platform in the data center for many years. They can certainly be that platform for automotive. SUSE was first in bringing them to the data center, and we do our best now to stay the same so that everything else can change also for the automotive industry. So how can automotive software platforms get to where the modular engine and drivetrain toolkits already are? First, the dozens of ECUs in the vehicle have to be consolidated into more centralized infrastructures. Only then can what is now firmware become application software running on a real computer. And remember, the best part always is no part. Second, to make the platform work, hardware enablement needs to move from BSPs or board support packages provided by the hardware vendor to the Linux upstream kernel and other open source projects. That's the only reliable way to ensure Linux as a platform is hardware agnostic enough to make sense. Finally, the software that used to be a firmware binary installed directly on a small ECU will become a reusable component, or what we call a containerized vehicle function. So, how do we envision that cloud-native car? And how do we envision those containerized vehicle functions? Well, basically, we think that we can reuse and leverage the proven concepts of cloud-native development. We think that edge use cases in industry, automotive, and retail have a lot in common. Even though it may not look like that at the first glance, it's basically always the same. First, develop on an engineering workstation, then test in a local or remote cloud, and finally deploy in the car like you would deploy the workload in a public cloud or at the edge. So how are we doing it? There's a whole separate session called Clash of Titans that was recorded for Tuesday, where members of our A team discuss the challenges of applying open source to the automotive industry. So I'll skip that part and dive directly into some of the other things that we are currently doing. First of all, to reach the necessary standardization and code sharing, industry alliances are a good first step. Let me mention 3 of the initiatives SUSE has joined to help reach that goal. SOFI could be the most important one. Its goal is to develop the blueprint for a scalable open architecture for embedded edge. This is highly aligned with our vision of the cloud-native car that runs containerized vehicle functions. The second one is a more recent initiative, Eclipse SDV. SDV stands for Software Defined Vehicle. It has similar focus, but it wants to give a new home to existing software projects and new projects that can contribute to the future of software-defined vehicles. And finally, ELISA. ELISA is an attempt to bundle the efforts of enabling Linux for safety applications. We are also building our own first full-stack demonstrator that will allow us to show the basic concepts of how containerized vehicle functions could work on real hardware. We've started with what you could call the Raspberry Pi car, because in the current supply chain situation, Raspberry Pis are, let's say, less unavailable than real ARM-based automotive hardware, and they come close enough to demonstrate the basics. Of course, we'll enable a variety of actual automotive system-on-chip architectures over time. In addition to that, we are investigating existing and upcoming frameworks for automotive software workloads like AUTOSAR, Adaptive, or ROS2 in the context of running them on our automotive Linux. There's also a lot of stuff going on at SUSE outside the automotive teams that will contribute to the value of our offerings to the automotive customer. Building a truly secure supply chain will be a key enabler to meet the new cybersecurity process and software patching requirements. SUSE has been using proven processes to secure the open source supply chain for many years. And just recently, we have documented how those processes meet the new SALSA or SLSA requirements framework. You may have also heard about our efforts to rethink enterprise Linux with our project called Adaptable Linux Platform. Our automotive team actively contributes to building this new platform so that it meets many of the requirements of Linux at the edge, and more specifically in the car, out of the box. In other words, we aren't looking at Linux in the car in isolation, but making sure that the ALP project lets us build an adaptable automotive Linux platform as well. As a concrete example for the car, we may want to pick lightweight container orchestration, at least for certain use cases, rather than go all in with a full-blown Kubernetes. Those options may then also be interesting for other edge scenarios, and so we are discussing them in the context of the Adaptable Linux platform. Now, I've mentioned before that not everything is great. Our journey into automotive has been a bumpy ride. Let me bring back a previous slide. We agreed that to be successful, we need to build a platform that is more centralized, move hardware enablement to the Linux upstream project, and containerize our firmware. Well, the OEMs or automakers do understand the need for a platform, but it seems as if most of them try to build their own platforms instead of collaborating on one. And while doing so, they often embrace the spirit of open source only half-heartedly and want to keep as much of their own secret sauce as possible. The system-on-chip vendors are another challenge. Like in the data center world, where new components or CPU generations are usually enabled in the upstream Linux kernel long before the hardware is released to the market, the use of vendor-specific board support packages is still the default. And as I've frequently put it in previous talks, those BSPs are evil. They prevent the larger ecosystem from working at its full potential because it becomes difficult, sometimes impossible, to support a certain SOC with a generic kernel. In many cases, you'll have to create and maintain one-off firmware-style operating system builds that are stuck to the exact kernel versions the BSP supports. And just like the OEMs don't want to share their secret sauce, many SOC drivers aren't open source, or at least not fully open source. Finally, from the OEMs to the tier 1 automotive suppliers to the SOC vendors and automotive suppliers, basically everyone has plans to take the whole cake of the software-defined car. And this leads to several challenges. Competing in-car architecture blueprints. Automakers pick one-to-one alliances with particular SOC vendors, which will secure their supply chain, but it won't help with getting industry standard hardware. And many hardware and software interfaces aren't well defined yet. Finally, because of the want-it-all approach, it's not really clear where unnecessary reinventing the wheel ends and true innovation that adds to the brand's value starts. That has to change. Because the open source cake works differently. As all the software is shared, you don't have to compete for your piece of the cake. Instead, the idea is that everyone together can bake a bigger cake, bigger than any of the individual pieces could be. Then you can have your cake, the whole one, and eat it too. There are quite a few open questions we need to work on. What is the right modularity for in-vehicle functions? Do containers, as used in the data center or cloud, match best, or do we need to find smaller or larger units for the car and only use containers as an inspiration? How can we achieve a truly hardware-agnostic stack, but not at the cost of losing the benefits of dedicated accelerator hardware? Scoping or right-sizing the hardware needed for a certain set of in-vehicle functions. Getting the hardware sizing wrong is very hard to fix later in the embedded hardware development process. We've identified that as a key challenge for our customers and are looking into solutions. Being able to test run and benchmark workloads in the cloud will help with sizing the production hardware. Which leads us to the last item, testing and simulation. To fully leverage the vision of a cloud-native car, where code is tested in the cloud before it's installed on an actual car, any input and output, like radar sensors, cameras, power steerings, or brakes, need to have digital twins that can be used at test or simulation time. Now, let me wrap up with a few thoughts about research that we still need to do at SUSE and as part of the larger community efforts. Linux wasn't developed with functional safety in mind, but it's the flexible and open platform automakers want, so it will be key to find new ways of certifying Linux for functional safety. The most promising approaches seem to be to build certification directly into the development, testing, and software build processes, so that costly recertifications can be avoided and newly added contributions can be gated right when they hit the kernel. As part of the SOFI initiative's blueprint, it has become obvious that vehicles will have to run highly safety-critical applications next to less critical applications. The orchestrator, the Kubernetes for the car, if you want, needs to be aware of that and schedule the right workloads into the right hardware, be it a high-performance core or a real-time core. And finally, the software stack on a single compute node in the car needs to get smaller. I've already mentioned the option of using alternative lightweight container orchestration. But there's also a new idea that looks promising, running WebAssembly binary code directly in sandboxes, without the need of a full Linux container. Again, if done right, those can be scheduled and orchestrated just like containers, even though they are technically containerless. To wrap up, we at SUSE think that the cloud-native car that integrates seamlessly as an edge device into a larger IT infrastructure from the car to the core to the cloud can become a reality. And we are ready to support you now if you're interested in taking that road with us.